196 countries across the world have come together to set a very ambitious, but obviously very necessary agenda and commitment to ensure that the global temperature does not exceed 1.5 to 2 degrees increase. Now, this is a very necessary agenda for a sustainable future, and different jurisdictions are interpreting or coming up with different action plans on how to decarbonize. So, for example, the EU has set a target of reducing greenhouse gas emissions by 55% over 1990 levels by 2030. And the UK has recently increased that target to ensure that the greenhouse gas emissions are reduced by 68% over 1990 levels by 2030. And here in Dubai, in the UAE, the commitment is to ensure that renewable energy supplies 44% of all energy needs by 2050. Now, some more statistics will show the need for heat and the thermal energy challenge in all of this. For example, 50% of all energy use in the UK is associated with heat, maybe space heating, domestic hot water, and different industrial applications. In the UAE, and actually across the GCC, 70% of peak electrical demand is attributed to space cooling, so the cooling of buildings and the environments in which we inhabit. But across the world globally, 90% of all energy use can be somehow associated to thermal energy. So whether that is for different applications at different temperatures, and whether the ultimate use is for heat or not, the carbon emissions associated with thermal energy are very significant. And to reach these ambitious targets that are being set out in COP21, to ensure that we can address and mitigate the effects of climate change, we must rise to the thermal energy challenge. So I'm here in the sustainable city today. It is in the UAE, where the temperature this summer is likely to reach the high 40 degrees or maybe even hit 50 degrees Celsius at some point over the summer, because it is a good example of what a more sustainable future might look like. One where we can still hope for a very high standard of living, but in a very sustainable way. It also characterizes the approach that many researchers in Heriot-Watt and beyond are taking to ensure that we are developing technology that can coexist with people and how they use it to ensure that they can live more sustainably, while they still insist on a very high standard of living. So as I go through this talk, I will explain some of the design approach. I'll also go to the metrics that we use to ensure that at the very early stages of any design and research that we're taking, that we are able to develop technology that is sustainable, that is having minimal environmental impact, and that it is addressing directly the decarbonization of thermal energy. I'll then try to highlight some of the contributions that my lab in particular is doing, mostly in collaboration with some high growth SMEs, producing technology that can have a huge effect worldwide. To have the maximum impact in any design innovation, it's really important to think about your approach. And in this case, where we're trying to decarbonize thermal energy, what we need to look at is not necessarily kilowatt hours, but we try to focus on the service level needs of an individual or of a community or even of industry. What do I mean by that? Well, really it is to stop thinking about kilowatt hours and kilojoules as units of energy, but instead to say, well, the need often, especially in domestic settings, is for thermal comfort. So to make sure that we have an environment in which we can sit and live in that is comfortable. Now, it's worth thinking then just briefly about, well, how does the body itself regulate its own temperature? It is quite a sophisticated machine, essentially, that is able to maintain a very precise core temperature of about 37.5 degrees, plus or minus 0.1 or 0.2. And it does this in very different environments of different temperatures. And it does it when it's under stress. You may shiver or you may sweat. Your peripheral vascular system will either dilate or restrict, your heart rate will change, and it works hard to ensure that that core temperature is maintained kind of irrespective of your environment. So whether you're here in the UAE reaching very high temperatures up to 50 degrees, or in the UK where it can easily during the winter months get below freezing and certainly towards minus 10 degrees, essentially the body is able to cope however under a stressed condition. But what's happening there is to emphasize that it's actually more about heat than it is about temperature. So what the body's doing is it's metabolizing. In each cell of our bodies, we are generating heat. That heat must be removed to ensure that we keep this delicate balance between the rate at which we produce heat and the rate at which that heat leaves the body. And that essentially, whether it is biomimicry, has to be the exact same approach that we take when we are designing renewable energy systems. Are we able to create environments that are thermally comfortable? Not necessarily, again, have this much heat addition or this much heat reduction, whether we're in the UK or in the UAE. But importantly, that we're getting that balance right. And that balance can be achieved in very many different ways. We should look back before we were so reliant on electricity and borrow from technology that is millennia old. And to a certain extent, that happens here in the sustainable city, just by having a look around at the color of the buildings, where glazing is placed. There's many facades here, for example, that have no glazing, something that is actually unusual in the built environment these days, because overall, the renewable energy, the demand for energy to maintain thermal comfort in sustainable city would be less than half of what it is in an equivalent dwelling that is less sustainable here. So to emphasize the point, it is really how do we approach design that will have the ultimate effect. And if we focus on generating more or converting more energy, whether renewable or not, and if we focus on economics or if we focus on efficiency, we might be missing a trick. Because by reducing and by looking at service level needs, we open ourselves to many more avenues of innovation. So if the approach to research and design is important, well then absolutely so too are the metrics that we use to assess whether a design, first of all, is effective, is it doing what we want, and also could it be any better? And by taking this kind of prospective look at the early stages of design, then we can ensure that we can achieve maximum impact with our decarbonization of thermal energy agenda. So there is something called a 4E model, and one metric would be efficiency. And obviously, we want devices to be as efficient as possible. Are they taking, for example, in solar power and converting it as efficiently as possible? Now, standard solar panels, depending where you are in the world, will operate at different conversion efficiencies. Typically, you'd buy them at maybe 22% conversion efficiency. However, in operation, they might work at anything from maybe 7 to 14%. However, higher efficiencies are available. And you will see that the latest technology is showing conversion efficiencies in excess of 44%. But these are not economically viable solutions, not currently at least. So that brings in a second metric. How financially viable or how economically viable is a solution? And can you take that as a metric from the beginning to help you design solutions, design systems that can be economically viable? Now, a third one that is particularly relevant for solar thermal would be the term exergy. So exergy, together with availability and grade, these are all kind of terms that we use in thermodynamics to define how useful or how suitable thermal power is for a particular application. So domestic hot water typically needs to be around 42 degrees, or ambient environment, we like to hold it somewhere between 20 and 25 degrees. But the question is, when we have a solar thermal device, as an example, is it able to produce that amount of heat at the temperature we want, and particularly when we want it? And these are all metrics that we need to be cognizant of from the very beginning as we go through any design process. And actually, one of the sums that we will use in solar thermal will be solar fraction. So to what extent can a device a solar thermal device produce the thermal energy you need throughout the year. What proportion of your thermal energy needs can be produced or delivered by that thermal energy device as a ratio. And that would be our solar fraction. Now, a fourth E would be the environment. And this is where we try to take a full life cycle analysis for any renewable energy system. So from the extraction of raw materials that might go into the manufacture, the transport, installation of a device throughout then its full life cycle or its full life operation and maintenance to its eventual decommissioning and recycling, then how much energy was embodied in that process? And that brings in a fourth E. So these metrics, when we're looking at the efficiency, the economics, the exergy, and the environment, need to be considered in equal weight at the early stage of any design process or any intervention to make sure that the impact of this intervention has a positive effect and serves the decarbonization of thermal power agenda. Now, one example that we can look to where perhaps this wasn't taken might be in the feed-in tariff that was launched in the UK in 2010. This is a very generous scheme that was designed to stimulate the solar photovoltaics market, and it certainly worked. Essentially, for every unit of energy that was produced by a domestic dwelling, the owner would get something close to 50 pence. And this very much stimulated the PV market. However, it had a very negative effect on the solar thermal market, which had a less, well, it didn't have at the time a renewable heat incentive, and when it did come in was not nearly as lucrative. So what happened essentially was a very step change in the market, where solar photovoltaics took off. But as a technology that might have an operation efficiency of 14% and only addressing maybe 20 to 25% of the energy bills of a domestic setting, it replaced nearly overnight solar thermal systems as part of a market share, which had a much more potential to mitigate thermal energy decarbonization. And these technologies, of course, are or can be up to 80% thermally conversion efficiency, but operationally typically around maybe 50 to 60%, but still addressing a much larger proportion of the energy demands of that domestic setting. So by taking a 4E approach, where you in equal measure consider the economics and the efficiency and the exergy, and of course the environment, then different decisions are made, and ones that we need to make to ensure that we're able to directly address the decarbonization of thermal energy. So my team and I have been very lucky to work with some high growth and innovative SMEs across Scotland and the UK, all developing solar thermal technology as part of a system to reduce the cost of solar thermal energy. Now, one such company is Salterby. Salterby was quick to realize where the cost goes when you're developing a solar thermal system. So as you can see from the graph here, 38% of the cost of a solar thermal system is attributed to the installation. And if adding together some of the standard componentry that can also be reduced and simplified, so at Salterby were able to show that a solar thermal system could be reduced in cost by 50%, especially for the retrofit market. Now that still presented some challenges. Some of the simplifications could inevitably compromise the solar to thermal conversion efficiency. And essentially that is the role that the university and the researchers play in ensuring that the high performance of a Salterby system is competitive with the leaders in the market. So with complementary solar test site facilities in the UK, in Edinburgh, and in the UAE, in Dubai, we're able to play a role in characterizing the performance of the Salterby system, enhancing its performance, and ensuring that it is ready for ultimately key mark certification and preparing it for commercial sales. So what we do essentially is to install a standard Salterby system on our Edinburgh campus at a northern latitude and to observe its performance across a duration in time, typically a year, to determine how it's performing in the environment in which it ultimately has its market, where there is demand for solar thermal hot water. And how it performs in freezing conditions, how it performs when there is such intermittency of solar energy is all very important to its ultimate contribution to this solar fraction. But when developing the actual technology itself, when looking at some of the components and how we can couple the collector to the ultimate destination, the heat sink, the water and the thermal store, this is where we can bring in some extra expertise through our advanced numerical modeling techniques, coupled with our testing in near idealized conditions in the UAE. We're able to bring those together to optimize the design and ultimate performance of the Saltropy system. And I'm very pleased to report how incredibly well Saltropy is doing now in installing systems across Scotland and the UK. SolarisKit is a second company that we are currently working with. And SolarisKit has taken a different approach with a really innovative design of a solar thermal system. Their primary market currently is to look at replacing kerosene and the burning of dangerous, effectively, materials in Rwanda and other countries across sub-Saharan Africa. Now, one of the key enablers or USPs for the SolarisKit is the fact that it's actually flat packable. So the idea that you can simplify the design to the point where it can be easily transported, easily assembled, and then effectively connected to deliver hot water was really the challenge that SolarisKit approached. Again, the university plays and our research group plays a key role in ensuring that we can optimize the coupling between the solar gain. So we're able to ray trace or to track the sun and understand how the sun is going to interact with the heat exchanger. And then also, as that heat is absorbed, how it can be effectively convected, taken away from the absorber into the hot water stream. And we're also currently working on advanced controller technology that, together with Internet of Things and artificial neural networks, we will be able to optimize their performance so that essentially these systems will learn from each other and become more and more sophisticated. A third challenge that we are addressing is solar fraction. So as I explained before, it is essentially the ratio of the amount of heat that can be delivered by a solar thermal system over the total demand for heat in, let's say, a domestic setting. Now, really, to achieve 100% solar fraction will include thermal storage. It's not a capacity issue. Thermal storage can be scaled easily. However, it needs to deliver the heat on demand and when it is needed. So as you can see from this graph, the demand for hot water, let's say, it peaks in the morning, minimal during the day, peaks again in the evening. And this is exactly the inverse of the solar resource, which obviously peaks in the middle of the day as the sun translates across the sky. So thermal storage will be key to making sure that we can move this peak in solar resource to meet those demands for thermal energy or hot water. Now, standard thermal storage, maybe a hot water tank with stratification layer, can easily translate this solar resource to that peak in the evening. However, it is much more difficult to keep a high-grade, high-temperature hot water overnight to address the peak in the morning. It's innovative companies like Sunamp, however, who've developed phase change heat batteries. These are very compact, very energy-dense thermal energy batteries that can store high-grade heat for long periods of time. And because they're small, they can be easily insulated and make sure that that heat is maintained until it is needed. Coupling phase change heat battery with solar thermal, therefore, has the potential to address this limitation on a daily basis. One of the key challenges, though, of course, is the rate at which we're able to charge and discharge heat. So often, renewable energies are relatively low power. However, coupling with thermal storage will accumulate the heat that can then be discharged at a high power, at a high rate, at the temperature that you want it to be. So it's going to play a key role in ensuring that solar fraction can be increased. Now, doing this on a daily basis will probably increase solar fraction potential up to maybe 65, 70, 75%. However, the holy grail has to be to achieve a solar fraction of 100%. In 100% solar fraction would mean that you would not need auxiliary systems. Now, auxiliary systems essentially just lend themselves to higher capital costs and higher capital investment, and overall keeping up the price of renewable sources of heat. So, to be able to achieve 100% solar fraction from a renewable source, therefore, is going to need interseasonal storage. So if we can manage this on a daily basis, how do we raise to the challenge of managing it and supplying heat on an annual basis? Solar thermal systems, of course, do operate in winter. They do in the UK. They will raise temperatures from maybe 4 degrees to 24 degrees, even on the coldest days. However, to get a higher temperature uplift up to maybe 42 degrees, auxiliary systems are currently needed. Now, interseasonal storage, thermochemical, for example, is something that we're working on to see if we can store the excess heat that we can accumulate during the summer months and provide it into the systems, into the supply or into the demand over the winter months. Heat transfer and thermal engineering have a role to play in renewable energy systems, far beyond just the production and provision of heating or cooling in different systems or in domestic settings. The temperature of operation of many renewable energy systems are very dependent on their overall performance. So, for example, a solar photovoltaic panel has a temperature coefficient, effectively meaning that its solar to electrical conversion efficiency reduces as the temperature increases. And here in the UAE, you can expect a panel during midsummer to be operating in excess of 80 degrees Celsius. And it's one of the contributory factors, together with dusting, that will reduce its conversion efficiency in operation to maybe 7%. In northern latitudes, like in the UK, you can expect conversion efficiencies to be in and around 14% due to lower ambient conditions and generally cleaner panels because of raining. But because of the lower solar irradiance, the yield still is perhaps not as high as it potentially could be. So what are we doing to address these challenges? Well, we're coupling photovoltaic panels with thermal panels. So a PVT panel has the potential to maintain the panel temperature much lower and maintain a higher conversion efficiency, but also harness or collect that thermal power and use it later for a domestic or other low-grade thermal application. And this is very important. This kind of synergistic combination of technologies is very important to addressing some of the thermal energy challenges and decarbonization of thermal energy. One further application then, of course, is storage. Now, no matter what renewable energy resource is out there, it's likely to be intermittent. Some may be more predictable than others, but it's never considered to be base load. For it to have a more significant role within the provision of the renewable energy from the grid, it will need to have a more stable provision. And this can only be achieved with battery storage. So what we're working with in particular are lithium-ion batteries, which are playing a more and more and a greater role in everyday application, whether it's your mobile phone, your Tesla Powerwall, or your electric vehicle. Lithium-ion batteries are new and enabling technologies for all of these. But as you charge and discharge them, they generate heat. They also need to be maintained at a very stable temperature, somewhere between 25 and 30 degrees Celsius, to ensure that they do not degrade too much over their lifetime. So by thermally managing lithium-ion batteries on a cellular basis, we're able to extend their life, improve their performance and round-trip efficiency, but also therefore reduce the cost of a unit of energy because there's less capital investment in the technology. So these are some of the ways in which we, in our thermal engineering lab, are contributing to the decarbonization of solar thermal engineering. So it is clear that if we are to meet the challenge of mitigating the effects of climate change, that we will need to decarbonize thermal energy. And while new technologies have a critical role in that, and the kind of design thinking and the different metrics that we need to employ to make sure that we optimize the potential of our innovations, we still should not lose sight of the fact that technologies have been around for many generations and hundreds and thousands of years. Technologies like are on show in the Sustainable City, and as you pan around, you will see this plaza that has employed these wind towers to ensure that this plaza is kept at a very hospitable temperature. So even during the very high temperatures of summer, that we can still get about and enjoy the outdoor environment. Similarly, Riccarton has similar old technologies. Ice from the loch used to be taken and stored in an ice house and used for the preservation of food over the summer months. So while we strive for new and innovative ideas for the future, we should also take advantage of the technologies of the past that can help us to decarbonize and ensure that we have a much more sustainable future.